Hey, welcome back. In this video, we're going to discuss permutations and combinations more. So when we talked about permutations and combinations in past videos, we dealt with factorials and binomial coefficients. We saw a lot of identities involving binomial coefficients in the last video. The permutations and combinations that we'll look at in this video, though, are a little bit different. The ones that we saw before, all of the elements that we were permuting over or finding combinations of were distinct elements. In this video, we're going to look at situations where we have some repeated elements. So if we get a problem where all of our elements are distinct, such as finding the number of ways to permute the letters A, B, C, D, and E. A problem like this, we've already seen problems like that, we know how to do them. The number of ways to permute those letters, we can solve that by writing some blanks for the letters and looking at how many choices we have for the first letter. We have 5 choices for that. Depending on what we chose for the first letter, we can't use that choice for the second letter, so we have 5 choices for the second, depending on the first. And then 3 choices for the third, depending on the first and second. And then times 2 and times 1 for the fourth and fifth. So that gives us 5 factorial. Now, we can generalize this. How many ways are there to permute the letters A1, A2, up to A sub n? So we can do that same idea with the blank slots for the letters. This time we have n blank slots. The first letter, there's n choices. Second letter, n minus 1 choices, because we can't use what we used for the first letter. Third letter, n minus 2. And it continues like that all the way down to 1. And that gives us n factorial. So when we're permuting a set of distinct letters, finding the number of permutations is just calculating a factorial. What happens though if some of the letters are the same? For example, here's a typical kind of problem you might see when you're trying to find the number of permutations of something with repeated elements. Find the number of ways to permute the letters of the state Mississippi. So let's look at that problem on the next slide. So we want to find the number of ways to permute the letters of the state Mississippi. First thing we can do to make this problem a little easier to work with is we can resort the letters of Mississippi to make them easier to count. So we'll group the same letters together. So we'll start with the M. We only have a single M. We then have 4 I's. We'll group them all together. We also have 4 S's. We'll group them all together. And finally, we finish with the 2 P's. Now, since we already know how to deal with permuting sets where all the elements are distinct, we can turn this state name right here, Mississippi, or the way I've written it is like Miss B. We can turn that into a set of letters, all of who are distinct. And the way we do that is we rename the I's into I1, I2, I3, and I4. So the I's right here, I turn them into I1, I2, I3, and I4. Same with the S's there. I turn them into S1, S2, S3, and S4. And these P's right here, I turn those into the P1 and P2. So all I did is I took the letters that were repeated and I gave them some subscripts to make them all distinct. Now, next thing I'm going to do, since I want to find the number of permutations of the state name Mississippi, I can first find the number of permutations of this new word that I just constructed that has each of the repeated letters with an added subscript to make them distinct. And that one we already know how to do. All the letters are distinct there. So the number of ways to permute that one is just the number of letters in it, factorial. It has 11 total letters, so it's 11 factorial. And that is what we have on this bullet. And then we can try to figure out how the number of permutations of the original word, Mississippi, or the resorted version of it, MISP, right here, how many permutations of that one do we have compared to the number of permutations of this one? So by what factor do the numbers of permutations of this and this, by what factor do these two differ? So in order to figure out that factor, we can look at some permutation of this first one. The first one where the letters are repeated and we don't have the subscripts. For any permutation of that first one, there's going to be a total of 4 factorial times 4 factorial times 2 factorial permutations of the second one corresponding to the permutation of the first one. So given any permutation of the first one, we can look at the locations of the i's in that permutation. And for any given locations of those i's, there are going to be 4 factorial ways that we can order the I1, the I2, and the I3, and the I4 in the slots for those i's. Given a permutation of this one, there's going to be some slots for the s's as well. There's going to be 4 factorial ways to order the s's, S1, S2, S3, and S4, and the slots for the s's from this permutation. Moreover, there's going to be 2 factorial ways to order the p's in this permutation right here. So the 2 slots for the p's, there's 2 factorial ways we can place the p1 and the p2 in those slots. So the total number of permutations of the second one, where we have the subscripts corresponding to each permutation of the first one right here, is just going to be the product of these factorials, which is 4 factorial times 4 factorial times 2 factorial. And that's exactly what we got in this box right here. So the claim is that the number of permutations of this first one is going to be the number of permutations of the second one divided by this quantity, the 4 factorial times 4 factorial times 2 factorial. And so we can calculate that. So we already found the number of permutations of the second one with the subscripts. That was just 11 factorial. And we're dividing that by this factor we just got here. 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. And we can simplify that to 34,650. So that's the number of ways to permute the letters of Mississippi. Here's another similar one. How many ways are there to permute the letters of the state Montana? So we'll start out by writing Montana in an order where we group the similar letters together. So we got 2 N's here, we got 2 A's. Everything else is distinct. And first step, like we did on the last slide, we'll make all these letters distinct. So we'll add subscripts to the N's and to the A's. So the N's turn to N1, N2, the A's turn into A1, A2. When all these letters are distinct, we already know how to find the number of permutations of that word with the subscripts. That's just the number of letters in it factorial. So 7 factorial, that's 5,040. And then we can do like what we did in the last slide. So we can look at each permutation of Montana without the subscripts. And then we can look at the permutations corresponding to that one of the second version where we add the subscripts. So if we have a permutation of Montana right here, there's going to be 2 slots for the N's and there's going to be 2 slots for the A's. And the 2 slots for the N's, we have 2 factorial ways to put the N1 and the N2. We can put them in either order. And the 2 slots for the A's, we also have 2 factorial ways to order the A1 and the A2. You can put them in any order. So the number of permutations with the subscripts right here is going to be 2 factorial times 2 factorial times the number of permutations without the subscripts. And we already found the number of permutations with the subscripts. That was this 7 factorial right here. So if we want the number of permutations without the subscripts, which was the original problem, we can just take 7 factorial and we can divide it by the factor that we found right here, the 2 factorial times 2 factorial. So 7 factorial over 2 factorial times 2 factorial, and we get 1260 for that. So 1260 permutations of the letters of Montana. So here is a problem for you to think about. How many ways are there to permute the letters of California? Now, let's move on to combinations. So here's a typical combination question when all of the letters are distinct. How many ways are there to choose 3 letters without repeat from the letters A, B, C, D, E? And we've seen how to do this in previous videos. So we have 5 total letters, they're all distinct, and we're choosing 3 of them. So this is our binomial coefficient, 5 choose 3. This is equal to 5 times 4 times 3 over 3 times 2 times 1. And I just want to emphasize, for combinations, I mean, you already know this probably from the previous video, but order does not matter. So when we choose these 3 letters in the first bullet, we can think that we're choosing these 3 letters at the same time. We're choosing them all at the same time, so we can't repeat any. And the order does not matter if we're doing them all at the same time. So like I said, the number of ways to choose 3 letters from the letters A, B, C, D, E is just 5 choose 3. And more generally, if we have n letters, A1, A2 up to AN, and we want to choose 3 letters without repeat, and we want the order not to matter, this one's just going to be n choose 3, and that equals n times n minus 1 times n minus 2 over 3 factorial, which is 3 times 2 times 1. More generally, we can look for the number of ways to choose k letters without repeat from the letters A1, A2 up to AN, where order does not matter. And this one is just n choose k, which equals n times n minus 1 down to n minus k plus 1. All of that over k factorial. Another way to write that is n factorial divided by k factorial times n minus k factorial. This is all stuff we've seen in previous videos, so this should just be some review. And the question is, what happens if we have repeats? So let me clear a little so we can look at that. So for example, in the simplest case, how many ways are there to choose 3 letters from AABB without using any copy of a letter more than once? So we're allowed to use a letter more than once, so we can use 2 A's or 2 B's. We just can't use any copy of a letter more than once. So we can't use this A right here more than once. We can't use this B right here more than once. But it's fine to have 2 B's because we have 2 copies of B. So we're going to try to count these number of combinations where we allow repeats. The order still does not matter here. And for this problem, it's simple enough that we can just list all of these combinations out where we choose 3 letters. So the only possibilities are going to be AAB and ABB. Again, because order does not matter. And because each letter, we only have 2 copies of the letter to use, and we need to pick 3 total letters. So the answer we're looking for here is just 2. Here's another similar kind of problem, a little different on the set. Suppose now our letters are A, A, B, B, B. So we have 2 A's, but we have 3 B's. How many ways are there to choose 3 letters without using any copy of a letter more than once? So we can use letters more than once, we just can't use any copies of letters more than once. Again, the order does not matter. Here, for this one, again, we could just list them all out. So the ones that work are AAB, ABB, and BBB. So we can have all of them B's. We can't have all of them A's though, because there's not enough A's. So we can have at most 2 A's because there's only 2 A's. And in that case, we have to have a B with it. So we get a total of 3 of these possible sets of 3 letters. And when I say set, set's the wrong word. I should call them multi-set because we're allowing elements to occur multiple times inside the multi-set. So now let's look at a slightly larger one. Let's say we have a set now. Our set right here, it has a total of 5 copies of A and a total of 8 copies of B. And we want to look at the number of ways to choose 7 letters without using any copy more than once. Again, the order does not matter. So we see that we could use all B's for our 7 letters because we have 8 B's. We could also use down to 2 B's. So if we use 2 B's, we can use 5 A's with those. We can't use 1 B because 1 B, we wouldn't have 6 A's. There's not enough A's. So we can do anything from 7 B's. We can do 6 B's and an A, all the way down to 2 B's and 5 A's. So the number of A's can go from 0 to 5. The number of B's can go from 7 to 2. So 7, 6, 5, 4, 3, 2. We can look at how many numbers we just said, or 0, 1, 2, 3, 4, 5. How many numbers did I just say there? Either way, the number of numbers that I say is 6. So that's the number of ways to choose 7 letters from this set with 5 A's and 8 B's if we only use each copy at most once. So the method that we're using here, it's fine if we have only 2 distinct letters. So that should say works. It's fine for 2 distinct letters, but what happens if there's more than 2 letters? Like if we had C's or D's or something like that in there. So we're gonna look at a more general method that will work better for more letters. So for this more general method, we'll start with a simple case where we just have 2 letters, just to illustrate the method, and then we'll apply it to some more interesting problems. So let's look again at the problem that we were looking at before. We have a set of letters that just has 2 A's and 3 B's, and the question is, how many ways can we choose 3 letters from this set without using any copy of a letter more than once? Again, I'll mention the order does not matter. So we're going to use a more systematic process for doing this one. We're going to use something called generating functions. And we're going to use these a bunch in the next few videos, especially when we're talking about partitions. And this will be the first time we see them. So this is kind of a simple use of them. And the idea of generating functions is that we have some sequence. And the sequence, we can encode it as the coefficients of polynomials. And what we're going to do here is we're going to work with multiple sequences encoded as the coefficients of polynomials, and we'll use them to evaluate other sequences that we're trying to find. And those sequences we're trying to find, we'll be able to read them off from the coefficients of polynomials. So let's see, what does that mean more precisely? And also I'll mention that the reason why we're going to use polynomials here is because polynomial arithmetic is going to allow us to simplify our work a lot and to do a lot less work than we would do just by applying a brute force technique. So in this case for this problem where we have 2 A's and 3 B's. So 2 A's and 3 B's right here. For this problem, we're going to have a polynomial which will represent the possibilities for our number of A's, and we'll have a polynomial which represents the possibilities for the number of B's. The polynomial for the number of A's, they'll just be called P sub A of X, and next to each power of X, we'll write the number of ways that we can have that number of A's. So we have a total of 2 A's. So it's possible to have 0 A's, that's fine. And there's one way to have 0 A's, it's just having 0 A's, that's the only way. So 1 times x to the 0. We put a 1 next to the coefficient of x to the 0, because there's one way to have 0 A's. Similarly, for the x to the 1, since we have 2 A's, it's possible to have 1 A, and there's one way to have 1 A. We just have 1 A. So the coefficient of x to the 1 is 1. Now, the coefficient of x to the 2 here, how many ways to have 2 A's? Well, we have 2 A's there. So the only way to have 2 A's is just having the 2 A's. So coefficient's 1 here. But now something different happens for the x to the 3rd. X to the 3rd, how many ways to have 3 A's? Well, we only have 2 A's right here. It's impossible to have 3 A's. So there's 0 ways to have the 3 A's. So coefficient x to the 3rd, 0. Coefficient of x to the 4th is 0. Coefficient of x to the 5th is 0, and so on, going forever. And we can think of this polynomial as being an infinite polynomial where all of the coefficients after x squared are 0. So we can write that just as 1 plus x squared. And note that x to the 0 is 1, so that's why we got the 1 right there.
We can do a similar thing for b, but I'll mention before we get to b that in this polynomial p sub a, the coefficient of x to the I, like I said, it's just a number of ways that we can have I copies of the letter A. So we can only have I copies of the letter A for I equals 0, 1, or 2 because we only have two A's to use. We'll do something very similar with B. We define a polynomial which represents the possibilities for the number of B's. This looks like the one for A, 1x to the 0 plus 1x to the 1 plus 1x to the 2, but then the x to the third term is different. We get 1x to the 3 because we have, up here, we have a total of 3 B's. And so that means there's a way to get 3 B's. There's one way. However, there's no way to get 4 B's, so we have 0x to the fourth, 0x to the fifth, and so on. So all the coefficients after x to the third are zeros. And this simplifies just to 1 plus x squared plus x cubed. And like the polynomial p sub a, in the polynomial p sub b, we can see that the coefficient of x to the I for each I is just a number of ways that we can have I copies of the letter b. So we have coefficients of 1 for all I from 0 up to 3 because there's 3 letters b, and then all I above 3 have coefficients of 0. Now, if we want to find the number of ways to choose 3 letters from this set, A, B, 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 all we have to do is multiply these two polynomials, p sub a and p sub b, and find the coefficient of x cubed in that product. This gives us all the possible ways to combine a way of choosing JA's with a way of choosing 3 minus j b's for each j from 0 up to 3. So if we evaluate this product right here, what do we get for that product? We can just multiply it out. So if you want, you can multiply by hand. It's probably better though, use a calculator or a script or some website like Wolfram Alpha. And when you multiply it, you get x to the fifth plus 2x to the fourth plus 3x cubed plus 3x squared plus 2x plus 1. And we just want to find the coefficient of x cubed. Coefficient of x cubed in there, we just can circle it. It's that 3 right there. So that's our answer. And we can use this method for any kind of problem like this. So let's see some other ones that are similar. I'll clear this so we can do them. So here's one that we saw before. Suppose now our set, it's that problem again where we have 5 A's and 8 B's. So 5 here, 8 here. And we want to find how many ways can we choose 7 letters from the set without using any copy more than once. Order does not matter again, and we'll use the generating functions. So we'll define some polynomials again, p sub a and p sub b. P sub a this time, it has coefficients of 1 for each power I equals 0 up to 5. So 1x to the 0, 1x to the 1, 1x to the 2, 1x to the 3, 1x to the 4, and 1x to the 5. That's because we have 5 A's. The x to the 6, however, has a 0 coefficient. Same with x to the 7th and so on. So all the coefficients above x to the 5th are 0. And that's because we have 5 A's. You can't have more than 5 A's. And when we simplify that, we can just write that as 1 plus x squared plus x cubed plus x fourth plus x to the 5th. The polynomial for p sub b, we can evaluate that just by looking at the number of b's. And we write the coefficients. It's possible to have 0 b's, and there's one way to have 0 b's, so we get 1x to the 0. It's possible to have 1 b, and there's one way to have 1 b, because all the b's are the same letter. So 1x to the 1, 1x to the 2, only one way to have 2 b's, because again, all the b's are the same letter. So 1x to the 2, 1x to the 3, 1x to the 4, 1x to the 5, 1x to the 6, because again, there's 8 b's we can use. 1x to the 7th, 1x to the 8th. But now we look at x to the 9th. Its coefficient. This one's going to be a 0 because there's 8 b's. You can't have 9 b's. You can only have at most 8. So all the coefficients after that are 0. And we can simplify that to the sum 1 plus x squared all the way up to x to the 8th. And we'll use the same method we used on the last slide. We take these two polynomials, we multiply them together, and we look at what is the x to the 7th coefficient this time, because we're choosing 7 letters. So we want the x to the 7th coefficient. And the x to the 7th coefficient in this product, 1 plus x squared up to x to the 5th times 1 plus x squared up to x to the 8th. We can multiply them together and we get this polynomial. So x to the 13th plus 2x to the 12th plus 3x to the 11th plus 4x to the 10th plus 5x to the 9th plus 6x to the 8th. So notice the coefficients went from 1 to 6, just went up by 1 for each one. Then it stays at 6 for a while. We get 6x to the 7, 6x to the 6, 6x to the 5, and then it goes back down again. 5x to the 4th, 4x to the 3rd, 3x squared, 2x, and 1. So we're trying to find the coefficient of the x to the 7th. That one is right there. It's 6 right there. And that's our answer. Coefficient of x to the 7th is 6. So this is the number of ways that we can choose 7 letters from this set with 5 A's and 8 B's without using any copy more than once. So we saw a couple of examples where we only have 2 distinct letters. Let's look at one now that's a little more interesting, where we have more than 2 distinct letters. Here's one where now we have 3 distinct letters. So we have 5 A's, 4 B's, and 3 C's. We still want to choose 7 letters from the set without using any copy of a letter more than once. I keep on calling it a set. The word I should be using again is multi-set, because sets have distinct elements. Multi-sets, you don't necessarily have to have them distinct. But in both of them, in both sets and multi-sets, the order does not matter. So again, I'll say that order does not matter. And we'll use the generating functions. We'll define p sub a here. This one is just the polynomial 1x to the 0 plus 1x to the 1 plus 1x squared plus 1x cubed plus 1x to the 4th plus 1x to the 5th. And then the rest of the coefficients after that are zeros. And that's because we have 5 A's. We define a p sub b polynomial. P sub b is just going to be 1x to the 0 plus 1x to the 1 plus 1x squared plus 1x cubed plus 1x to the 4th. All of the coefficients after that are 0. That's because we only have 4 b's. So 4 b's, 5 a's, and we only have 3 c's. So that gives us the coefficient of the polynomial p sub c. We get 1 plus x squared plus x cubed. So all the coefficients above 3 for p sub c are 0. And all we want to do here, same methods on the previous slides, we just want to multiply these polynomials together and look for the coefficient of x to the 7th, where that 7 is the number of letters that we're choosing. So the coefficient of x to the 7th in the product PA, PB, PC, we just multiply those 3 polynomials together. 1 plus x squared up to x to the 5th, 1 plus x squared up to x to the 4th, and 1 plus x squared plus x cubed. Multiply them together. You can use Wolfram Alpha if you want, or a calculator, whatever you feel like. And when we multiply it, we get this polynomial. So this one goes up in the coefficients more quickly than the last one. So we have x to the 12th, then we have plus 3x to the 11th, plus 6x to the 10th, plus 10x to the 9th, plus 14x to the 8th, plus 17x to the 7th, plus 18x to the 6th. And then they go back down. So 17x to the 5th, 14x to the 4th, 10x cubed, 6x squared, 3x, and 1. And we wanted the coefficient of x to the 7th. I circle it right there. So it's just 17. So instead of doing a brute force solution with a lot of cases, all we have to do is just multiply a few polynomials together and look at a coefficient. So this saves us a lot of time compared to our other method that we had for solving this. So here's a problem for you to think about. How many ways are there to choose 9 letters from this set, which has 6 A's, 7 B's, 2 C's, and 3 D's? And we don't want to use any copy of a letter more than once, and order does not matter. So order does not matter on that last one. Maybe I'll even write that. Order does not matter. Just to emphasize. Okay, and I'll clear that so we can look at the next slide. So let's look at this word R combinations. We've actually already been looking at a bunch of R combinations, but we should define what this term means. So when we have one of these problems where we have a bunch of letters, maybe some of the letters are repeated, we can think of these letters, like I was saying before, as a multiset. A multiset is different from a set because you're allowed to repeat the elements, but the order still does not matter. So order does not matter, but we're allowed to have repeated elements. When we're choosing our letters from the multiset, and we're not using any copyable letter more than once, all we're doing is taking a sub-multiset of this set of size R. So a sub-multiset is analogous to a subset. So we can think of an analogy. Sub-multiset is to multiset as subset is to set. We can even write that up here, kind of like they used to write it on the SATs. Subset is to set as sub-multiset is to multiset. So we have that analogy you can keep in mind. So the key is that the subset, all the elements in the subset are contained in the set, and all of the elements in the sub-multiset are contained in the multiset. The set is not allowed to have repeated elements, but the multiset is allowed to have repeated elements. And both of them, the set and the multiset, order does not matter. And that goes the same for the subset and the sub-multiset. And so we're going to call this sub-multiset of size R an R combination of our multiset. So if we're trying to count the number of R combinations of S, our multiset S, all we're trying to count is the number of sub-multisets of S of size R. So that's all an R combination is. It's just a sub-multiset of size R. And for example, these are some of the R combinations we've done on the previous slides. We found that the number of 3 combinations of A, B, 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 that multiset, is going to be 3. We also found that the number of 7 combinations of the multiset with 5 A's, 4 B's, and 3 C's is 17. So these are some R combinations that we did on the previous slides. Let's look at some others. So let's consider an R combination where our multiset, S, has infinitely many A's and infinitely many B's. We want to figure out in general, for any R, how many R combinations are there of S. So we'll use the same method we used on the previous slides. We'll define these polynomials, P sub A and P sub B. This time P sub A, since there's infinitely many A's we can use, we have a coefficient of 1 next to every power x to the I. So it's possible to have any possible number of A's, IA's for any I. And there's only one way to have IA's because all the A's are the same. So we get 1x to the 0 plus 1x to the 1 plus 1x to the 2 and so on up to going forever to infinity. So we can write that as a sum I equals 0 to infinity of x to the I. We get the exact same polynomial for P sub B. So we can write both these polynomials, P sub A of x and P sub B of x, as the sum I equals 0 to infinity of x to the I. And I'll just write as the same exact thing as P sub A of x. So P sub B and P sub A, they had the exact same polynomial. And like on the previous slides, all we're trying to do here, counting the R combinations, is just find the coefficient of x to the R. So same R as we have here in the product PA times PB. And we can see that the coefficient of x to the R in this product, it's just the sum of the products of the coefficients in PA and PB whose power of x sum to R. So let's look at that in a little more detail. So up here, we will have our PA of x, and here we'll have our PB of x. So we get 1 plus x squared, and so on, up to, and we'll throw in the x to the r minus 2 here, x to the r minus 1, plus x to the r, and so on, all the way up to plus, and it goes forever, so it's infinite. Same with PB of x, we'll have our 1 plus x squared, all the way up to x to the r minus 2. So the exact same thing we have for the PA. I'm just writing these terms in here just because we're going to be pairing up some terms, so it'll be helpful to have some of them written to look at. And it goes forever.
So if we're trying to find the coefficient of x to the r and the product of these two, when we multiply these two together, the coefficient of the x to the r is going to be the sum of the products of the coefficients that we get by combining a term from PA and a term from PB whose powers of x multiply to x to the r. So like the term 1 here, this is an x to the 0 term. This has to be paired with the x to the r term in PB. So these two pair together. This x term right here has to pair with the x to the r minus 1 term from PB. Those two pair together. The x squared right here pairs with the x to the r minus 2 term. Those pair together. And we just keep on going like this through the dots. And then we get the x to the r minus 2 pairs with the x squared here. So those pair. X to the r minus 1 pairs with the x here. And finally, that x to the r right here pairs with the 1. And we can notice that any of the larger terms out here in the dots, they don't affect the x to the r term of the product at all because they're too large. Once you have a term in PA or PB whose exponent is greater than r, it's impossible for that term times some term in the other polynomial to give you an exponent of r. So the only terms contributing to x to the r are these terms in PB and these terms in PA. If we want to find the coefficient of x to the r in the product, we just take the sum of the products of the coefficients in these pairs that we made. So each of these pairs, the 1 and the x to the r, that pair, each of the coefficients in it is 1. So the 1 is just 1 times x to the 0. The x to the r is just 1 times x to the r. Similarly, this pair, the x and the x to the r minus 1, coefficients in both of those are 1. X squared and x to the r minus 2, both coefficients there are 1. We can just think of that as 1 times x squared, 1 times x to the r minus 2. So all the pairs of coefficients are just a pair of 1s. We're just taking the sum of the products of these pairs of 1s, and we're adding up that sum. So the powers that we're using from P sub A, we can look at those powers. We started at x to the 0 with that 1. We go all the way to x to the r. So we're ranging from x to the 0 to x to the r. Same with the P sub B, x to the 0 to x to the r. And note that when we use x to the j from P sub A, we're combining it with x to the r minus j from P sub B. So the x to the 0 went with the x to the r, the x to the 1 went with the x to the r minus 1, x to the 2 went with the x to the r minus 2, and so on, all the way up to the x to the r going with the x to the 0. So x to the j goes with x to the r minus j. And so we add up the products of the coefficients in these pairs. And like I said, all of these coefficients are just 1. So we're just adding up 1 times 1, and we're going from j equals 0, 0 right here, to r. So the sum is j equals 0 to r right there of 1 times 1. And notice that that sum has a total of r plus 1 elements in it. So if we're going from 0 to r, we're including 0, we're including 1, we're including 2, all the way up to r. So that's a total of r plus 1 terms in our sum. And it's just r plus 1 terms, each of which are 1. So we get a total of r plus 1. So the number of r combinations of this S, where we have infinitely many A's and infinitely many B's, is just going to be r plus 1. Another way we can write r plus 1 is as r plus 1 choose 1. That seems like a funny way to write it, but it's going to be helpful for noticing a pattern on some later slides. So we have an r plus 1 choose 1 right here, and we'll see some other binomial coefficients on the next few slides. Now, I guess I'll clear that so we can look at the next slide. So here's another set. It's the next set that it's natural to look at. So we just looked at a multi-set which had infinitely many A's and infinitely many B's. Now here's a multi-set that has infinitely many A's, infinitely many B's, and infinitely many C's. Same question as the last slide. How many R combinations of this multi-set? And we'll use the same method here. So we're going to define some polynomials for each of our letters. Our P of A polynomial will be the same as on the last slide. It's just going to be 1 times x to the 0, plus 1 times x to the 1, plus 1 times x squared, plus 1 times x cubed, plus 1 times x to the 4th, and so on forever. Because any possible number of A's is possible because we have infinitely many A's. So any non-negative number of A's is possible. And each non-negative number of A's can occur in one way because all the A's are the same. So we have coefficients of 1 for every x to the I from I equals 0 to infinity. So that simplifies to the sum from I equals 0 to infinity of x to the I. And that's the exact same polynomial we get for P sub B and for P sub C. They're all the exact same polynomial. And we're trying to find the coefficient of x to the R in the product of these polynomials, just like all the previous slides. So we're just trying to find the coefficient of that x to the r term when we take this product. And this product, we can write it in a simpler way because all the PA, PB, and PC are the same polynomial. So since all of them are this polynomial, sum I equals 0 to infinity of x to the I, the product of the three is just that sum raised to the third power. So that's all we're doing there. And on the last slide, we found that the product PA of x, PB of x is equal to the sum I equals 0 to infinity of I plus 1 times x to the I. Why is that? Well, the previous slide, we found that the number of R combinations of this set, infinity times A, infinity times B, is R plus 1. The way we calculated that is we showed that the x to the r coefficient in this product, I equals 0 to infinity of x to the I squared, is r plus 1. So that's how we calculate the number of R combinations of the multiset with infinitely many A's and infinitely many B's. We just took the x to the R coefficient of this product, the sum from I equals 0 to infinity of x to the I, that quantity squared. And so that tells us, since this product, the sum I equals 0 to infinity of xi, quantity squared, since that has an x to the r coefficient of r plus 1, what is that saying? If the x to the r coefficient in that product is r plus 1, then that's telling us that the product I equals 0 to infinity x to the I, that sum squared. So it's telling us that product is just equal to the sum, we can say j equals 0 to infinity of j plus 1 times x to the j. So if the x to the r coefficient in this product right here is equal to r plus 1 for each r from 0, 1 up to infinity, then that's telling us that this product right here of these sums, so the sum squared, is just equal to this polynomial down here, which is the sum j equals 0 to infinity of j plus 1 times x to the j. Because that's the polynomial whose x to the j coefficient is j plus 1, which is the same as the polynomial whose x to the r coefficient is r plus 1. So that's how we get that PA of x times PB of x is equal to this summation right here. Because that summation, sum I equals 0 to infinity of I plus 1 times x to the I, is the same as this summation right here. We're just using an I instead of a j. So we're going to use this fact. So since we're trying to find the x to the r coefficient in this product right here, we're trying to find the coefficient of x to the r there. We can actually find the coefficient of x to the r in a simpler product where we take this one, we write this one as the sum I equals 0 to infinity of x to the I squared times itself. So sum I equals 0 to infinity of x to the I. So we had the sum cubed, and we just write it as the sum squared times the sum. And the sum squared, we use the fact that we proved on the previous slide that that sum squared is equal to this, the sum j equals 0 to infinity of j plus 1 times x to the j, which we can also write as the sum I equals 0 to infinity of I plus 1 times x to the I. So we just substitute for this, we substitute this right here. And this part is the exact same. So that's all we did to get from that bullet to that bullet, just some substitution. So now we want to look at the coefficient of x to the r in that product, the product on this previous bullet right here. And that's going to be the sum of the products of the coefficients in these two polynomials whose powers of x sum to r. And these two polynomials, again, are just the two in this previous bullet. So the sum I equals 0 to infinity of I plus 1 times x to the I, and the sum I equals 0 to infinity of x to the I. And the powers that we use in that first polynomial, the sum I equals 0 to infinity of I plus 1 times x to the I, since we're looking for the coefficient of x to the r on the product, the relevant powers in the first polynomial are just going to be the powers from x to the 0 to x to the r, because any greater powers are not going to contribute anything to the product, the coefficient of x to the r on the product.
And if we use the term x to the j from that first polynomial, the sum I equals 0 to infinity of I plus 1 times x to the I, we'll combine it with an x to the r minus j from the second polynomial to make x to the r. So let's look at that in a little more detail, kind of like we did in the previous slide. So we'll write our two polynomials. So our first polynomial is this one, I equals 0 to infinity of I plus 1 times x to the I. Second polynomial will be this one, I equals 0 to infinity of just x to the I. And we'll write them like this. So we get 1 times x to the 0, we'll say, plus 2 times x to the 1, plus 3 times x to the 2. So I'm just writing the sum out, plus so on, plus, then let's look at our x to the r minus 2 term. So we'll have an r minus 1, x to the r minus 2, plus r, x to the r minus 1, plus r plus 1, x to the r, and so on forever. And then this one down here is simpler. We got 1x to the 0 plus 1x to the 1 plus 1x to the 2 dot 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 up to 1x to the r minus 2 plus 1x to the r minus 1 plus 1x to the r plus dot 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 forever. Keeps on going. And we want to multiply these two together and then look at the x to the r coefficient of that. So the 1x to the 0 term, to get an x to the r, we'd have to pair that up with 1x to the r over here. So these two get paired up to make an x to the r. The 2x to the 1 right here, that gets paired up with the 1x to the r minus 1. The 3x squared right here, going to get paired up with the 1x to the r minus 2. So in general, we're pairing up the x to the j term from the first polynomial with the x to the r minus j term from the second one. So this r minus 1, x to the r minus 2, we're going to pair that up with the 1x squared down here. And this r, x to the r minus 1, that gets paired with the 1x to the 1. And similarly, this last one, the r plus 1x to the r, this last relevant one. Of course, there's going to be more terms after that, but they're irrelevant to the x to the r coefficient in the product. That last one that's relevant pairs with this 1x to the 0. And we just want to add together the products of these pairs of coefficients to find the coefficient of x to the r and the product of the polynomials. And so we can see that that sum of the products is just going to be the sum from j equals 0 to r again, because we can use any power x to the I for I equals 0 up to r. So j equals 0 up to r of, and this is going to be the sum of the products of the coefficients in these pairs. So we can look at, for j equals 0 in this top sum, when I had a 1x to the 0, I paired that with a 1x to the r down here. J equals 1, I had a 2x to the 1. I paired that with a 1 on the bottom. So when I multiply them together, I'm getting the coefficient from the top times a 1 from the bottom. So the bottom coefficients are all 1s. So the top coefficient is what we need to put into our sum. And the top coefficient for each j, for j equals 0, the coefficient is 1. For j equals 1, the coefficient is 2, and so on. So we saw that the coefficients are just j plus 1 for each j. And when I write this in terms of i's, it's I plus 1. So since it's written in terms of j's down here, I just need to put a j plus 1 down here. And I can simplify that sum. So that sum, I can write it as 1 plus 2 plus 3 all the way up to j plus 1. And so we know how to evaluate that sum. We've done this sum a couple times, at least in class. So that's going to be j plus 1 times j plus 2 all over 2. Another way to write that is just as j plus 2 choose 2, which is interesting because on the previous slide, we saw j plus 1 choose 1. And for this one, we're seeing j plus 2 choose 2. So if we had k distinct letters in our multiset and infinitely many copies of each one, a natural conjecture would be to make that the number of r combinations is going to be just the r plus k minus 1 choose k minus 1. So let's see if that continues. but there's a little more on this slide to mention. So let me clear that work that we just did. So that work that we just did, we saw this sum right here. Oh, and this sum, the way I've written it right here, there's a small typo here. So this j plus 1 at the end, this should be an r plus 1. So that should be an r plus 1. This should be an r plus 1 times r plus 2. So we got r plus 2 choose 2 here. So those should be r's, not j's. So we got r plus 2 choose 2, which looks like our previous slide where we got an r plus 1 choose 1. And now let me clear that to show the last bullet. So the sum of the products of the coefficients in the first polynomial and the second polynomial, whose powers of x sum to r, we just showed that we got for that sum the exact sum I wrote, the sum j equals 0 to r of j plus 1 times 1. And again, that sum right there is just 1 plus 2 plus 3 all the way up to j plus 1, or sorry, r plus 1, not j plus 1. And that gives us r plus 1 times r plus 2 over 2. And again, that's r plus 2 choose 2. So that's how we got r plus 2 choose 2. And again, I'll mention the pattern we saw. So on this one, we saw an r plus 2 choose 2 for the number of r combinations of this multiset. And here we had 3 distinct letters in our multiset. On the last slide, we had 2 distinct letters, and we saw r plus 1 choose 1. So let's see if the pattern continues on the next slide. So next slide, we'll consider the general version of this problem. We have this multiset S, and the number of distinct letters is k this time. So we have an a sub 1, a sub 2, a sub 3, all the way up to a sub k. And we have infinitely many copies of each letter. So the question is, how many R combinations do we have of S? And we're going to prove by induction on k being the number of distinct letters, that the number of R combinations is R plus k minus 1, choose k minus 1. And we already saw this is true for k equals 2 and k equals 3. So we already proved this is true for k equals 2 and k equals 3. So we could make those our base cases of the induction. We'll just make the base case k equals 1 though. So for k equals 1, our set, the multiset S, is just A1, infinitely many copies of it. And the number of R combinations of that is just 1. So since all the A1s are the same, there's just one way to have R A1s. So that's going to be R choose 0. And we can see that R choose 0 is equal to R plus 1 minus 1 choose 1 minus 1. So that's our base case. For the inductive hypothesis, we're going to have this assumption that the number of R combinations, in the case when we have k distinct letters, A1, A2 up to AK, with infinitely many copies of each, the number of R combinations in that case will be R plus k minus 1 choose k minus 1. So this is what we're trying to prove, and we just need to show that the next step of the induction is also true for this quantity. In other words, we're trying to prove that the number of R combinations, so what we want is that the number of R combinations of this set, infinity times A1, infinity times A2, up to infinity times A sub k plus 1. We want to prove that this is equal to R plus k choose k. So that's our goal. And I'll put a question because we haven't proved that yet. So that would be the next step of our induction. So we want to use our inductive hypothesis to prove that this is true. And another way to say our inductive hypothesis right here, that there are R plus k minus 1 choose k minus 1 R combinations of this multiset. Another way to say that, as we've seen on the previous slides, is equivalent to saying that this product, the sum I equals 0 to infinity of x to the I raised to the kth power, this has coefficient of x to the r equal to r plus k minus 1 choose k minus 1. Another way to say that the coefficient of x to the r is r plus k minus 1 choose k minus 1 for all r is just saying that the polynomial is equal to this sum, I equals 0 to infinity of I plus k minus 1 choose k minus 1 times x to the I. So that's another way to state the inductive hypothesis. And so what we're going to try to prove, the thing that we're trying to prove that we haven't shown yet, we're going to try to show that the product I equals 0 to infinity of x to the I, this raised to the k plus 1 power, we want to show that the x to the r coefficient of this is just r plus k, choose k. So that's our goal. We're going to try to prove that. And so that's what we're doing. We're trying to find the coefficient of x to the r in this product that I wrote, this product of the sum I equals 0 to infinity of x to the I raised to the k plus 1. So this exact thing right here is what I wrote right here. We're trying to show that the coefficient of x to the r is r plus k choose k. So we're just going to evaluate that coefficient, and we'll hope that we get r plus k choose k. Now this product right here, the sum raised to the k plus 1 power, I can break up that power into the sum raised to the k times the sum. So anything to the k plus 1 is just the thing to the k times the thing. And that's what I'm using here. And in order to figure out this product, so the way I've written this product with two terms in the product, in order to evaluate that product, I can use a similar method to what I did on the previous slides. So I can just take the products of the coefficients in each of these terms. So the first term is the kth power of the sum I equals 0 to infinity of x to the I. The second term is this one, which is just the sum I equals 0 to infinity of x to the I. I just look at the sum of the products of the coefficients whose powers of x sum to r. Let me clear that a little so it's easier to read. So we just want to do the same thing we were doing on the previous slides. And just like on the previous slides, the relevant powers from the first polynomial, the kth power of this I equals 0 to infinity of x to the I, the only relevant powers are the powers from x to the 0 to x to the r. Same with the second polynomial. And if we use x to the j from the first polynomial, we're going to use x to the r minus j from the second polynomial. So if we want to find the sum of the products of the coefficients in these two polynomials whose powers of x sum to r, we can do this kind of similar to like we did in the previous slides. So let me write a little bit. So our first polynomial, we got I equals 0 to infinity of x to the I raised to the k power. And we'll use what we proved on the previous in our inductive hypothesis. So this is our inductive hypothesis. This is equal to the sum I equals 0 to infinity of I plus k minus 1, choose k minus 1, and this times x to the I. And I can get rid of that extra parenthesis, it's unnecessary. Okay? And similarly, the other polynomial I can write down here, I can write I equals 0 to infinity of x to the I. And we'll write both of these, so we'll put them one above the other. So this first one, so I'm going to get k minus 1, choose k minus 1 here, times x to the 0. So let me actually throw that x to the 0 on there. Plus k minus 1 plus 1, choose k minus 1. So we can write that as k times k minus k, choose k minus 1, times x to the 1, plus k plus 1, choose k minus 1, x to the 2, all the way up to, let's see what we got. So we'll have an x to the r minus 2 plus something x to the r minus 1 plus something x to the r. And then it'll go forever after that. And the terms after that won't matter. So the term next to the x to the r minus 2, its coefficient, we're just going to have r minus 2 plus k minus 1, choose k minus 1. So r minus 2 plus k minus 1, choose k minus 1. Then we'll have on this one, it'll be, let me put a little arrow to fit it in there, r minus 1 plus k minus 1, choose k minus 1. And the last one will also be choose k minus 1, and it will be r plus k minus 1.
choose k minus 1. And now our polynomial down here, we just have a 1x to the 0 plus 1x squared. Well, let's do the x to the 1 first. X to the 1 plus 1x squared plus dot 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 plus 1x to the r minus 2 plus 1x to the r minus 1 plus 1x to the r, and so on. Okay, now we'll do what we did in those previous slides. We're just going to pair up the coefficients whose powers of x multiply to x to the r. So we have the coefficient of x to the 0. We're going to multiply that with the coefficient of x to the r down here. I'm going to pair those two together. I'm going to pair these two together, coefficient of x to the 1, coefficient of x to the r minus 1. We're going to pair these two together, coefficient of x squared and the coefficient of x to the r minus 2. And we'll just keep on doing that. So we're pairing together the things that make an x to the r. And we'll just take all those pairs, we multiply the coefficients in the pairs, and we add up the products that we get. So we have a sum j equals 0 to r, and then what do we get in our products? So we get something times 1, and the something is the coefficients we're getting on the top for each j. So for each j, the coefficient we're getting is just j plus k minus 1 choose k minus 1. So the sum becomes, we can write the sum out. So at j equals 0, we just have k minus 1 choose k minus 1. At j equals 1, we have k choose k minus 1. J equals 2, we get k plus 1 choose k minus 1, and so on. So the choose part stays the same, but the thing we're choosing from increases by 1 each time until we go all the way up to r plus k minus 1 choose k minus 1. And we can recall that for a question like this, where we have a summation, where we're starting at something that's of the form, we can say z choose z, and then we get a z plus 1 choose z, and a z plus 2 choose z, all the way up to some, let's say, n choose z. We can use a certain identity for that. And the identity, we can see that identity with a nice picture. So let's say right here, here's our k minus 1, choose k minus 1. And then we go down diagonally 1 from there. So we got our k choose k minus 1 right here. And then we got our k plus 1 choose k minus 1, diagonally 1 down from there. And then we can make the triangle go more. So it keeps on going dot, 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 all the way down to, let's say, our r plus k minus 1, choose k minus 1. So we'll make that a pretty large triangle. So that's our Pascal triangle. We're only looking at a certain diagonal of it, starting from this right side, this right diagonal. We go down to here. And we showed in the previous video that if you take the sum of these elements of Pascal's triangle, it's going to give you the element down here. So if you do this one plus this, all the way up to plus that, we end up getting the one that goes right here, which is r plus k, choose k. So this sum, by the hockey stick identity, which we proved on the last video, we get for this sum just r plus k, choose k. And we proved that identity by induction in the last video. And this is exactly what we wanted to prove. So our inductive step, we were just trying to prove that the number of R combinations of the multiset where we go from A1, A2 up to A sub k plus 1. So the multiset with k plus 1 distinct letters, all of which occur infinitely many times. We were just trying to show that the number of R combinations was R plus k choose k. And that's exactly what we got here. We got R plus k choose k. And we just used the hockey stick identity to do that. And we combined the hockey stick identity with induction. So what we did on the previous slide, what we did there is just a special case of what we did here. So this sum that we did on the last line here, this is just a more general version of the sum that we did on the previous slide. And this works for any number of distinct letters. So now we see if we have any multiset like this, where all of our letters occur infinitely many times, and we have some finite number of distinct letters, then we can evaluate the number of R combinations of that multiset. So now that we see how to do that in general, and this last bullet here is just exactly what I said and what I wrote down. So when we take the sum of the products of the coefficients that we paired up, we evaluate that sum, and that sum gave us, like I showed, using the hockey stick identity, we just got R plus K choose K. So that completed our induction because that was proving the next step of the induction. So we proved the K plus 1 step, assuming that the K step was true. And again, I'll mention, we used the hockey stick identity. So that was the crucial method that we used at the end to evaluate the sum. And again, we proved the hockey stick identity in the last video. So if that seems unfamiliar, just check out the last video. And so here's one last problem for you to think about before this video is over. And this problem is just combining some of the types of problems that we saw earlier in the video. So I just want you to find the number of 7 combinations of this multiset, which has 2 A's, infinitely many B's, and infinitely many C's. And that's the whole video. So thanks for watching.